Hello friends, welcome to this lecture on the Jacobian and its application in double integrals. Why does and where does a Jacobian arise? Let's look into that. A Jacobian is a determinant which is used whenever you make a change in the coordinate system while evaluating multiple integrals over a region within the domain. So, to accommodate for the change of the coordinates, the magnitude of the Jacobian determinant is used as a multiplication factor within the integral. So this needs a little bit of explanation, which we will get into. That is, the area of a small region in the transform space is scaled by the Jacobian determinant to approximate areas of small images in the original space. That means we have the original space, then we have the transform space. The area elements in both of them strictly do not match, but on a microscopic scale, they can be made equal, and this is where the Jacobian plays a part. How do you represent a Jacobian? Suppose you're moving from the XY coordinate system to the UV coordinate system, for which you are given transformation equations. U is equal to f of xy, v is equal to g of xy. The Jacobian is now denoted by J is equal to dou uv by dou xy, which is determinant of the first order partial derivatives of u with respect to x and y. Ux and uy in the first row, vx and the vy in the second row, or the transpose of that. Let us visualize a Jacobian now. Let us take the simplest case where we have a region in the xy plane, which is a square in this case of sides 1 each. I will now transform using a linear transformation u is equal to 2x and v is equal to 3y. This, anybody can guess, can be seen as having a stretching effect. There's a stretch of 2 units in the x direction and 3 units along the y direction. So obviously the square does not remain a square but becomes a rectangle. So that's what we can see. There's a stretch of 2 units along the x-axis, u-axis, and stretch of 3 units along the v-axis. Now you can understand what is a Jacobian. In this very simple case, you measure the area in the transform space, that is the A prime, which is 6 units, and divide it with the area of the square in the original frame. So the area of that square is 1 unit. So A prime by A will give us 6 by 1, which is 6. So the Jacobian, if you calculate even through the determinant, produces the same number. So this can be a very simple way you can interpret the Jacobian, but while using linear transformations. When we have nonlinear transformations, J is very likely to be a non-constant. So when you represent the double integral now, the left hand side is the double integral in the original space in the xy frame, and the function f of xy gets transformed to a new function g of uv in the transformed space, and you can see the dx dy area element is not du dv but mod j times du dv. So the area element dx dy is transformed to mod j times du dv in the transformed space. And obviously this means that a change of variables should also be accompanied by fixing limits for the variables u and v. So the output of double integral f of xy dx dy will be the same as the output of double integration of g of uv into mod j times du dv. So that is a Jacobian. And why that modulus? Because dx dy is an area element, so area cannot be a negative number. Similarly, if you just attach j times du dv, there's every likelihood that j can be a negative number. So to compensate for that, to prevent such a situation from happening, so mod j times du dv is considered. Are there any coordinate systems which are frequently encountered? Yes, there are several of them. One of them is very popular, that is known as the plane polar coordinate system. And there are also other equally popular coordinate systems like the elliptic coordinate system, the parabolic coordinate system, etc. Of course, those are very special situations. Let us think about the plane polar coordinate system. Imagine you have got a point P with coordinates x comma y in the xy coordinate system, and then using two new variables r and theta, where r is the length of the vector joining origin to the point P and theta is the angle the radius vector makes with the x-axis. So simple trigonometry will give us cos theta is equal to x by r and sin theta is equal to y by r, giving us the transformation equations x is equal to r cos theta, y is equal to r sin theta, and the Jacobian using the determinant rule gives us r. So in the plane polar coordinate system, the Jacobian is always r. Now, what is the difference between the way you divide a Cartesian region and a polar region? In the case of Cartesian, you will recall that we had used horizontal and vertical lines to create rectangular pieces. In the polar grid, we use radial lines and concentric circles. So you can see here that we have used radial lines. Every 10 degrees, you can see one ray is coming out of the origin. And then we have also used circular arcs, circles, in fact, concentric circles, to create what is known as a polar mesh. So the way we divide the region matters. How do you convert from the Cartesian to plane polar coordinate system? As already explained earlier, when you take the double integral f of xy dx dy and you decide to convert it into polar, the new variables will be r and theta and the Jacobian is r. So the transformed integral will be double integral g of r theta times r dr d theta. So r dr d theta accounts for the area of the polar rectangle in the polar coordinate system. Then we have, as I've already mentioned, other coordinate systems like the elliptic coordinate system, for which the transformation equations are a little bit difficult. They involve hyperbolic functions, and you can see that it's an orthogonal system. We are not going deep into this coordinate system because we are not applying it, but this can be reserved for further study. Similarly, we can have the parabolic coordinate system. Oh my God. Similarly, we can have the parabolic coordinate system, which is also designed to be an orthogonal coordinate system. So these are the transformation equations from xy to parabolic coordinates. X is equal to rho times sigma times tau, and y is equal to half times tau square minus sigma square. So we will try to reserve this for a deeper discussion. but the focus will be on plane polar coordinate systems. One of the crucial properties of the Jacobian that will be exploited will be, suppose you start with the XY coordinate system and move to the UV coordinate system using the transformation equations u is equal to f of xy and v is equal to g of xy. You find the Jacobian of that. And then there is this interesting rule, which is what we call the inverse law or inverse property of Jacobian. J times J prime will always be equal to 1, provided J is not equal to 0. So J prime is nothing but dou xy by dou uv Jacobian. Sometimes we may need that for problem solving. So let us keep this as a very valuable property of Jacobians. So where are we heading after this? So we must understand what is the context for transforming a Cartesian double integral to a plane polar double integral. So we have to understand that. Understanding the dynamics of working in the plane polar coordinate system. That means how do you bring in the transformation? Then how do you fix theta limits and fix the r limits? And then we will see some related problems. So the next the detailed lecture is going to tell you everything about how to handle the plane polar coordinate system by converting a Cartesian double integral, which is not favorable for direct integration, but much easier in the polar coordinate system. So we'll be looking to meet at that particular lecture. Hope you understood this part of the discussion. Thank you.